Hi, welcome to es301 Engineering Analysis. This is Chapter 7, Roots of Polynomials, Part 2. So here are the two learning goals. At the end of this, you will have learned Muller's method for finding the roots of a polynomial, and you'll understand Baristow's method for finding roots of a polynomial. They're just two different methods, two different numerical methods, and you can use either one. So first, let's do a quick review about polynomials and polynomial deflation. So the goal, what we're attempting to do, is we're trying to find the roots of this polynomial equation, which means we want to find values of x for which that function is equal to 0. And the reason we care about this in engineering is that polynomials are the form of the characteristic equation, which occurs in ordinary differential equations, which describes how a lot of dynamic systems behave. Now remember, if I had some polynomial like that, knowing my values of x or seeing it is a little difficult. However, if I was to put it in a different form, for example, factor it this way, then it's very quickly easy to find out values of x for which this would be equal to 0. Clearly, -1, +4, etc. So those would be my values of x, or the roots of this polynomial function. Now, deflation involves finding one of those and then dividing by it. So, for example, if I was to take that polynomial and divide it by x - 4, after I've found the root is 4, I would have a new polynomial that involves those 4 terms, and then I would go ahead and find my next root. And I do that until I don't have any more roots to find in my function. Okay, so first I want to discuss Muller's method. And Muller's method is very similar to the secant method. So briefly remember the secant method for finding the roots of an equation. The secant method, what we did is we had some function, that's the black line that's being shown right up here, and we're trying to find the roots of that equation. And so what we did is we just took a guess value, for example this point, and then another value somewhat close to it. We drew a line through it, found out where it intersected that function, and then what we would do is then determine what the value of the function is and find out how close we were to that being equal to 0. And we would just keep refining our guess. We're going to do something very similar with Muller's method. The only difference is instead of fitting a straight line, what we're going to do is we're going to fit a parabola to it. And I'll explain why we're doing a parabola instead of a straight line in just a moment. And so again, what you're going to do is you've got your function shown in black that you're trying to find the roots of. You take a guess value, for example, this value of x2, and now you need to take two values somewhat close to it. Two values because we're fitting a curve to it, a polynomial. And then what we're going to do is we want to find out where that polynomial intersects the axis down here, and then find out how close we are to finding the root of the equation. And we're just going to go ahead and refining it. All right. Now, the reason we were fitting a polynomial, as we'll see, is that we want to be able to find complex roots of equations, which you can't do with the secant method. And to find complex roots, you need to have a polynomial, or you need to have a quadratic equation, or essentially a parabola like that. All right. So let's just kind of first look at this at a high level. What I've done is I'm trying to fit a parabola here, and so I can go ahead and describe a parabola with a second order equation where the function, this thing in blue over here, this is function f of 2, and I've got to find these three coefficients a, b, and c. And what I'm going to do in order to do it is I'm going to need three equations to find those three unknowns. Is I'm going to say the function, the black line, intersects the blue line at those 3 points right there. So effectively I'm saying f2 of x at x2 is equal to my function at x2. I do the same thing. f2 at x1 is equal to my function at x1, etc. I do it for x0. And the function is again, this is the black line. This is the function that I'm trying to find the roots of. I'm then going to have three equations. I did the same thing down here for x0. Three equations. Solve those three equations for my constants a, b, and c. And then I'm going to have an equation for what the blue line is. And then I'm just going to set that right there equal to 0, and then solve for the value of x that intersects right there. Okay? Now note, since I've got a quadratic equation I'm setting equal to 0, I'm actually going to end up finding two roots. I'm going to find this value here and this value here. My estimate I'm going to want is going to be the one closest to x2 right there. Now, we mentioned here, if, for example, what it turns out is that x is complex, I got a pair of complex conjugates, it turns out both of those are going to be roots of the equation. All right, so now let's go ahead and look at the implementation of this, get into a little bit of the nitty-gritty. And so first of all, this is all outlined in the book, so we'll go kind of quickly on it. First, you just define a series of constants, and they use h and delta. It doesn't really matter. And so what I'm doing is I've got my three guesses. I guessed x2 and then x1 and x0, usually just some numbers fairly close to it. And I'm just go ahead and defining some intermediate values h and then this function delta. This function that I'm using over here, f, remember that's the function I'm trying to find the roots of. Okay, so now I just have these four constants, h0, h1, delta 0, delta 1. And those are just some intermediate values, so now I can find those constants a, b, and c. So now I have the equation of the blue line. I've computed a, b, and c just using all those intermediate values that I found. And now I'm just going to go ahead and find out where that blue line, using the a, b, and c values, intersects the y-axis. And this is the equation that I do. And so this point right over here is x2. And so what I'm doing is I'm finding a value of x3. So this line right there is what the book calls x3. That's my new guess value that I have of where it intersects. All right. Now remember, this intersects at two different points, and you can see that because I'm going to essentially computing two values of x3. I'm going to compute a value there and a value there. So you want to pick the one that's closest to x2, so that's going to be your new guess. Go ahead and just get rid of the x0 value and keep shifting across. Now I'll use this x3, x2, and x1, and then iterate the whole process again until I go ahead and meet some sort of error criteria. So for example, my newest guess, x3 over minus x2, normalized by x3, is going to go ahead and be a less than some sort of stopping criterion, stopping error that I have. Okay, so now I'm going to just kind of quickly show you an implementation of this using MATLAB. And so this is for Muller's method. The first four lines right over here are just those constants, h0, delta 0, and delta 1. I'm calling those d0 and d1. Muller function is an external function. That's the function f of x is equal to something, something, something. I got that in an external file. This is the big, large polynomial that I have. The next three lines here, I'm just, again, using my intermediate values I computed to find a, b, and c. And now what I have over here, I call this dx1. What that is that's x3 minus x2. And remember, there's two different values of that. And so effectively, I find both of them, and then I determine which one is smaller. So where is x3 closest to x2? And then I'm going to go ahead and set that equal to my new value of x3. Now, let me mention, I'm using MATLAB, where if I have a vector, I can't have 0. So these is actually going to be like x1, x2, x3, x4. In the book, we have an x0, but since indexing starts at 1, that's why you see, for example, it looks like I'm finding x4. This would be the same as x3 in the book, because there's no x0. So then what I do is I run through this once. I'm going to have a new value of x. This is where I go ahead and just get the one, remove the one that's furthest up from the end. Go ahead and take my new estimate. I compute what the error is. Now it's become x3 because I cut off the one at the end. And then I can go ahead and just run this whole function again. So this, I don't have this quite in a loop. I'm just running this once, getting a new value of x. So maybe at the command line, I type in up here at the top this initial value for my value of x, and I'm going to each time compute new values as I rotate through. So for example, here would be a function, that Muller function that I have. It's just simply a polynomial, so it's just a two-line function. And what I'm doing is I'm trying to find the roots of that polynomial function that I have right there. Let's go ahead and look at this, and actually I'm running this in Octave. It runs just like MATLAB. And so this first line right over here, I'm just putting in my initial guesses that I have, 1.8, 8.5, and 9. And then I run that Muller method function, and what it does is it computes a new value of x, okay? And so what it did is that x3 value, the new one was 1.85. I went ahead and knocked off the one at the end and shifted it down, and there's my error estimate. And then I go ahead and I keep doing this as I move through, and if you notice after about running it 3 or 4 times, now I'm starting to get a complex value as my initial guess. So this is what's nice about Muller's method. You can't do with like secant and false position. I can actually find complex value. And so my error is still kind of large, so I'm just going to go ahead and keep running this. And if I keep running it, run it about another 10 or 11 times, now you realize my error has gotten very, very small. And then here are my roots, and you can see all 3 of these are the same because I've converged on it, and it's 1 minus 0.5i, which is one of the roots of that function. That tells me also 1 plus 0.5i is also one of the roots of the equation. At this point, you'd go ahead and deflate the polynomial, and then go ahead and run that again. Let's look at one other method. This is just an alternative numerical method you can use. This is Barstow's method, and this is really close to what we had in the previous video where we were doing long division. So I'm going to kind of present this first from a high level so you can kind of see the analogy with this with long division. So Barstow's method, what I'm attempting to do is I'm going to go ahead and take my polynomial that I want to find the roots of, that's what's underneath here, and then I'm going to divide it by another polynomial. I'm going to do actually a quadratic, and again I'm doing that because I want to go ahead and be able to find complex roots. But otherwise the steps are the exact same. So effectively what I have is I have an initial guess, a guess value of R and S that's going to go ahead and give me two initial roots. Right? So then you go through and you do all that long division. We did long division before. And you do it all down until you end up with some sort of remainder. And your remainder here, instead of being a constant, it's actually going to be something times x plus another constant. And the reason for that is because I'm dividing by a second order polynomial up here. Now what happened is, if I have a remainder, a non-zero remainder, it means that my guesses of R and S were not correct. My two values of my roots were not correct. I need to go ahead and adjust those. And we do that using a first order Taylor series. So I find new values of R and S that go up into that equation there, doing that first order Taylor series. And now I'm going to go ahead and just do again my long division, and I'm going to end up finding out what my new remainder is. And I keep doing that until my remainder is effectively 0. And so what I would do is I would compute the error, which is how much R is changing and S is changing. So I'm finding two roots at the same time. And out of that, maybe their error, both of those is less than some stopping error. And I call it E sub stop because this is the error in S. A little bit careful with the notation. Again, I'm sticking with the book, where R and S are my two values. Now once I've met that stopping condition, now I'm going to go find essentially what those two roots are. R and S aren't the roots, they're this equation. I use my quadratic equation to go ahead and find out what my roots are. And this is going to give me two roots from this equation. And now it's been effectively deflated at the same time. So now I'm going to have a new polynomial and I can go through. So you're finding two roots at a time. Okay, so let's kind of just look at the implementation of this now. So I'm going to get down a little bit into more nitty-gritty. Here again is the function that I have that I'm trying to find the roots of. And remember now, what I had was all that long division stuff. And so this is the way you can implement that long division. These are the equations you'll kind of see in the book, so I'll just kind of go through this quickly. This is all just effectively doing all that long division numerically. So first you're going to find some constants. The book calls it b sub n. And so I'm going to go ahead and find these values of b. And so first of all, I take the highest order coefficient here, make that b sub n, and then I'm going to find the next one down. Remember, n is just the order of the highest polynomial. I find this value, and then I go ahead and find a bunch of other b values as I goes from n minus 2 to 0. So I'm going to loop that part around. I have a bunch of b values. There's some intermediate values involved with the long division. I'm going to do something similar. I need to find some new values using that, which is my values the book calls c. So again, I find n and then n minus 1, and then I go ahead and go all the way down. This only cycles down to 1. And effectively what you're doing is you're finding those remainder values at each one of those intermediate lines in the long division. Now once I've done that, then I'm going to be able to go ahead and find out what my changes in my two roots are going to need to be. How much do I need to adjust delta R and delta S? And it turns out there are two simultaneous equations right here that I need to go ahead and solve both of these equations. I have my B1 and B0 that I got those right up in here, and I have my C1, C2, and C3 I got from there. Those are just intermediate steps required in order to get to this equation here. Now I need to solve it. It's kind of tough to solve simultaneous equations numerically in a computer that kind of operates it. What you could do is you could solve, for example, this top equation for delta R and plug that into there. You'd have an equation, find delta S, go back and plug it in. And so just a little bit of algebra here, you figured that out. We also mentioned, if you look at the pseudocode in the textbook, there's kind of another little trick that you can do it, kind of find them, and it's what's written with these three lines here. And this will effectively find the same thing for this right there. That is the delta R, that is the delta S value, using, again, just the values of C and D. So there's kind of the nitty-gritty implementation of Barstow's method in order to get that to work. All right, so let's go ahead and review what we looked at. What we did is we We looked at Muller's method and saw it's similar to the secant method, except we're fitting a quadratic function instead of a linear function. And we also looked at Baristow's method, just an alternative method. The nice thing about Baristow's is that it does deflate at the same time. Muller's method, you'd have to deflate after finding the root. And it involves guessing a pair of roots. You're doing that through your values of R and S, and you keep doing that until you get a remainder that's near 0. And one last thing to mention, the reason we do quadratic guesses, or effectively guess 2 roots at the same time, is it allows you for finding pairs of complex roots. You can't do that when you have false position in the secant method.